So my talk today, evaluation of drawdown dynamics and implications for groundwater detectability with remote sensing. I'm actually going to focus a lot on the remote sensing side of things. And, usually at the end of a talk, whoever's presenting says, and wow, isn't this great? This thing we can do now. Let's all go use it. And actually, today's talk is really around healthy skepticism. Um, more than anything, and how to appropriately use different tools. With that, I'll first say that I took this picture in 2015 at the height, or maybe the trough of the drought. And you can see the role that groundwater can play in green when it is available. And otherwise, sometimes we have the browns. So my background is in groundwater remote sensing using satellite observations to understand changes in groundwater systems. Many of you also study groundwater in different ways and with different tools. And so as you all probably know, groundwater is underground, and that has many benefits and also some challenges. And those challenges are particularly apparent when we think about how to use remote sensing observations to study groundwater dynamics. When I talk about remote sensing today, I'm referring to satellite observations, but anything from a handheld camera to a drone is a remotely sensed observation. But today, again, I'm focused on satellites primarily. This is some, but not all, of past and current Earth observing satellites. Many of these are NASA satellite missions, often in partnership with other agencies, either US agencies like USGS or international space agencies. And every single one of these satellites shown here is detecting something about the land surface or above. If you are interested in understanding anything below the land surface, we have just a small number of additional satellites. Most recently, SMAP, the Soil Moisture Active Passive satellite mission. These satellites are able to detect water changes theoretically in the top about 5 centimeters of the land surface. Some research has shown a little bit deeper, some shallower. But for the most part, the majority of our Earth observing satellites are looking at the top, dipping down into the land surface, top layers of our land and atmosphere interactions. If you, like me, like many of us, are interested in studying groundwater with satellite observations, then there's really only one satellite mission that is able to capture groundwater in any way. And you'll see that it is not an explicit observation of groundwater, but we have to play some tricks to isolate groundwater. So GRACE is the Gravity Recovery and Climate Experiment satellite mission, and I'll talk more about GRACE plenty today. But GRACE is able to detect changes in the total amount of water stored on land, including groundwater changes. But importantly, in general, and especially for the groundwater systems we have in the Northwest, GRACE doesn't know or care, frankly, if your groundwater system looks like this, just a nice, clean, unconfined aquifer, if there's a bedrock anywhere, hopefully somewhere, if you have a semi-confined aquifer system, or even a fully confined layer. So I call that job security, is the disaggregation of GRACE into component parts. And I'll talk in a moment about what that actually looks like. I'll just, before getting to that, talk a little bit more about the GRACE mission. GRACE is unique in Earth observing satellites in that it's actually a pair of satellites that orbit the Earth together, chasing each other around as Tom and Jerry, and the two satellites are nicknamed Tom and Jerry. The actual physical satellites themselves are about the size of a minivan, and they're spaced apart about 250 kilometers. And the actual observation, you can kind of see this visualization, is just the distance between the two satellites. So again, GRACE stands for Gravity Recovery and Climate Experiment. And the reason why it's named that is because the satellites are actually measuring changes in Earth's gravity on a monthly time step, or we say time variable changes in gravity. And because water is so heavy, the main thing that causes changes in Earth's gravity field on monthly to annual timescales is the large scale movement of water stored on land. So the GRACE mission was launched in 2002. It had a 5-year lifespan and it ended up exceeding that. Eventually the batteries on the satellites died and a GRACE follow-on mission was launched in 2018. And so we have close to continuous monthly data collected from, we started using it in January of 2003 to present day. So we have observations for an increasingly useful time when you're doing things like significance testing of trends. The GRACE data are on a monthly temporal resolution. So looking at how changes in gravity occur from month to month over, importantly, really large spatial scales. So full river basins, large aquifer systems. And at these large spatial scales, we'll get back to that, GRACE is able to detect changes in water mass of plus or minus about 1 centimeter spread across that entire area. So if you have an addition or subtraction of 1 centimeter of what we call liquid water equivalent over these large spatial scales, then GRACE is able to detect that change in water mass. So liquid water equivalent is just if you spread a volume of water out over a specified area, how deep would that water be? And then how is that changing? So really a remarkably high accuracy estimate for something flying in space, right? But as we'll see, maybe not high enough accuracy. On the left is an image of Earth's gravity anomaly, so deviations from the mean before GRACE was launched. GRACE was really launched to just better understand Earth's gravity field and not for hydrologic applications. After GRACE was launched, this was actually just a few months after, on the right, you can see that our understanding of where gravity anomalies were higher or lower really tightened up in resolution. So more specifically, the way GRACE is detecting these changes, again, these satellites are flying together as a pair. And as the front satellite comes up to more mass on land, the gravitational pull of that mass causes the front satellite to move further from the second satellite. So that front satellite is getting pulled down toward that mass, and the distance between the satellites is increasing. Now, let's say it snowed a bunch in a month, and now there's more mass on a mountain. As that front satellite comes up to that now snowier mountain, there's a stronger gravitational pull than there had been in the previous month, and the distance between the satellites increases in response to that monthly mass change. And then as it passes that, the satellites go back together. So as the satellites come up to where there had been more mass, the distance increases. If there's less mass in an area, the satellite distance will decrease. So there's really high accuracy to about the diameter of a human hair in terms of measuring the distance between the satellites that changes as a function of water stored, movement in water stored on land. Importantly, the GRACE satellites act as what we call a relative gravimeter, so they're able to detect changes in gravity, but not the total amount of gravity. So we cannot use these satellites to estimate the total amount of water stored on land, only how it is changing month to month, year to year. So we can do things like try to quantify if you're pumping groundwater, applying it to the land surface. Some will run off, a lot will evapotranspire. If it leaves that basin area, then there's a mass loss that would be detected in the satellites. So the way we apply this to the water cycle, this is a beautiful updated image of where we have water stored on and moving through the landscape. We just think of the basic water budget that kids learn about in school. And we have two different ways to formulate the water budget equation, both of which can be applied to the observations from GRACE. We can either think about anomalies or deviations from the mean in the storages or stocks of water. So here, capital S is the total water stored on land, and that's equal to the sum of anomalies and snow water equivalent, soil moisture, surface water, and groundwater. If you're in an area where glaciers are present, glaciers would be added to this water budget. Or we can think about changes in storage from month to month as precipitation minus evapotranspiration minus discharge, and then whatever groundwater flux in and out of your study area is present. So when we talk about anomalies, we're talking about length scales like millimeters or inches of equivalent water. When we talk about storage changes, it's a length per time, so a centimeters per month, a feet per month. So depending on what data you have, you can kind of play around with these equations in different ways. So then the GRACE observations would be equivalent to the total water storage change over some time period, or the anomaly in total water storage if you're working with stocks. I'm going to show you, this is from California. Sorry, I don't have a cool graphic like this for Washington yet, but I want you to see what the GRACE data look like. So on the right, we have the Sacramento San Joaquin River basins outlined in yellow here. And as this time series progresses, you'll see the spatial distribution of these water storage anomalies. So when you see more red, the area is drying or has less water than average. And then when it's blue, it has more water than average. The time series on the left is just the basin average of what you'll be observing. So I'll just let this run. So we're getting more water than usual, less water than usual, entering into some drought. We had a bit of recharge, and then we're descending into a deep multi-year drought that California experienced, big bad red, and then it snowed a lot and brought us back to that mean. So when we play with GRACE data, we can often play, I usually play with time series like this, or for large enough spatial areas, you can look at the spatial distribution of that water movement on the landscape. So now let's bring it home. Let's look at the Columbia Plateau Regional Aquifer System. And we're going to basically walk through what GRACE tells us is happening with groundwater storage change in the Columbia Plateau and how that compares to observations. So I'm going to be using this, the stocks form of the water budget equation, where the anomalies and total water storage are the sum of the component parts: snow, soil moisture, surface water, and groundwater. On the left here, you'll see the outline of the Columbia Plateau Regional Aquifer System, CPRAS. This is as delineated by the USGS ModFlow model. You see the Columbia River in dark blue with the Snake in green coming in and the Yakima River in yellow. And then in red are the locations of groundwater monitoring points that some of you on this call possibly are responsible for monitoring, where we have enough data that we can evaluate the ground-based observations compared to the remotely sensed observations. Now, an important thing to note is the spatial scale I mentioned earlier for GRACE. GRACE data can be downloaded and used on a very coarse spatial resolution. Coarse if you're used to doing anything useful with water management. So you can see, hopefully, there's sort of these white lines here making grid cells. Each of these grid cells is 100 kilometers by 100 kilometers. That's really the smallest spatial resolution that GRACE can be processed for. And even then, a single GRACE pixel is not really accurate. You have to look at a basin average. So there's only about 11 GRACE grid cells that cover the whole Columbia Plateau. It's a bit at the edge of the spatial scale that is viable with GRACE. So the way we use GRACE to study groundwater is just a simple bit of algebra. We're just going to take this equation and rearrange it to solve for groundwater. And then we use other things to subtract out the non-groundwater parts from the GRACE signal. So we get the total water storage anomaly from GRACE. This is our big S. In my work and in most people's work who use GRACE to study groundwater globally, some combination of models, maybe remote sensing, maybe observations are used to quantify anomalies in snow water equivalent and soil moisture. That's especially the case for soil moisture. We just don't have dense, large scale enough observation networks of soil moisture. I'm trying to change that, and I'll talk about that later. For snow, we can do a little bit better, especially in the Western United States with SNOWTEL. And then in this study area, we use observations and records, mostly from the US Bureau of Reclamation, on surface water storage changes from reservoirs and lakes. Altimetry is a satellite-based method to quantify changes in lake level, reservoir level for large reservoirs. So mathematically, again, it's simple algebra. We're just taking GRACE, subtracting out everything that is not groundwater, using whatever tools we have available. And then what we're left with is the anomalies in groundwater as observed by GRACE. Now, importantly, the other thing that ends up on the left-hand side of this equation is all of the uncertainty, all of the error that exists in these methods that gets propagated into and manifests in the groundwater signal. So what we're isolating as the groundwater residual, as we call it, also includes whatever error, whatever uncertainty is associated with the methods that you use to subtract out the non-groundwater components. And I call what's left over the groundwater bucket. I said earlier that GRACE doesn't care or really know if your groundwater system is unconfined, semi-confined, very confined, multiple layers of confined. As for us, what you get is just this amount of groundwater anomaly. And so then what I'm interested in knowing is how that relates to reality, and if that is something that we can do anything useful with from a management and application perspective. So my study area in this is, again, that Columbia Plateau Regional Aquifer System, again, delineated using the USGS groundwater flow model. The thing I love about this picture, so that's your land cover in the background, is that it really highlights that the CPRAS underlies the vast majority of cropland area in the Pacific Northwest, including the whole Columbia Basin project and Yakima River. We have the Snake River Plain, so there is other cropland area in the Columbia River Basin, but really the majority of cropland area sits almost perfectly within the aquifer system area. And so one of my big interests is in understanding how groundwater has been used in the past in irrigated agriculture and how that might be changing in the future. In order to understand the future, we have to make sure we can recreate the past appropriately. All right, so let's get back to that groundwater bucket to look at monthly changes in groundwater in the CPRAS as observed by GRACE. This is work that my now graduated PhD student, Collins Asante Sasu, did. So this is what the data look like when we do this disaggregation to isolate out groundwater. In the upper left, we're using slightly different acronyms. My deepest apologies for that. This is what GRACE data look like. So this is the basin average water storage anomaly of GRACE. And so you can see a clear seasonal pattern where we have increases in water storage in winter and decreases in the summer, as we would expect. We see a little dip in 2005 associated with the drought. And then a few other sort of little dips. Interestingly, the 2015 drought doesn't show up as strongly here as the 2005 drought. And then this gap is just the time between the first GRACE mission launching, or dying, actually, and the second, the follow-on launching. And then we kept that gap consistent with the other data sets. For soil moisture and snow, we used model output from a coupled hydrology and cropping systems model. If you've seen various presentations, for example, related to the long-term water supply and demand forecast project out of WSU and Jenny Adams' group, you have seen work from VIC. VIC is the variable infiltration capacity hydrology model that they couple to a cropping systems model to be able to represent things like the impact of irrigation on specific crop types, which are not well represented in most hydrology and land surface models. We thought that was important because irrigation obviously impacts total water storage variations. So that's manifested in the soil moisture observations here. And then we have our surface water anomalies from observations. And so right off the bat, you can see that based on these water budget components, just what's shown here, the majority of monthly water storage anomalies are driven by soil moisture variability. And then snow and surface water variability play a pretty small part here at a monthly time step. And then groundwater fills in the rest if you're conserving mass, which we are hopefully doing. So then when we isolate out that groundwater, this is what the data look like. Really the difference between these two lines, the blue and red, is just if you run the hydrology model by itself versus if you run it connected to the cropping systems model to better represent irrigation. And actually when you convert to anomalies, so remove the monthly mean from each individual month, those line up pretty tightly. And so again, with groundwater, we see clear seasonal variations. There's sort of a slight decrease, then a slight increase, kind of a slight decrease, but overall there's not really a clear trend in groundwater variability here. I love to look at monthly climatologies, and actually we'll jump to that here. So in black, we have the GRACE signal. In pink is groundwater, green soil moisture, dark blue surface water, cyan snow. So a climatology figure like this, for January, you take the average of all the Januaries in your record, the average of all the Februaries, the average of all the Marches, and it gives us a really nice, clear seasonal signal of the different water budget components. And you can see here that GRACE derived groundwater storage peaks sort of around April, May, and then has a low in September. And based on this, it actually shows that the groundwater signal is a slightly larger portion of the water budget than soil moisture is. So a bit more than half comes from groundwater. So then the question is how, it's great. We can make a figure. If you have data, if you have numbers, you can make a figure about anything. But really the question is how, actually I'll plot back here. How do these groundwater storage anomalies derived from GRACE compare to observations? Most of the groundwater observations that we have are on an annual time step, so taken in the spring to represent the spring high, sort of as close to an equilibrium condition as you can get. And so in order to compare the GRACE-derived groundwater storage anomaly to observations, first we converted these monthly anomalies to the spring high. So we took the average of the spring months for each of these years and compared annual to annual. And mathematically, here's what that looks like. When we take measurements or monitor groundwater, most often that's done and with the highest accuracy at individual groundwater wells. And what you're measuring is the hydraulic head, this H, or the potential head, or the potentiometric surface, however you want to call it. And so if you have multiple measurements over time, d by dt, then you can see how the water level or the head in your well is changing in time. That head, the depth to water in your well, is what you care about if you want to have water in your well, right? But to compare to GRACE, we have to convert those water level changes to groundwater storage changes. And we do that with this simple equation. So this is the groundwater storage change from GRACE. And then you have to multiply it by this storage coefficient. And depending on if your aquifer is unconfined, so open to the land surface, a direct pathway is available from where water hits the land surface or is sitting in a lake or a wetland or a river. Water can go straight down to the water table here. And I don't know if you guys can see my mouse. I'm kind of working under the assumption that you can. And then in an unconfined aquifer, when you pump water, there's storage loss that can occur directly where you are pumping. There's a little bit of storage loss that occurs first. And then if you can't balance out, or if the aquifer doesn't balance with recharge and discharge, that's a whole different talk. Then you have actual storage loss right here that's driven by gravity drainage. In a confined aquifer, so under an impermeable or essentially impermeable barrier, the head variation in the well is driven by pressure changes, and you don't have the same larger storage loss when you pump from a confined aquifer as an unconfined. So instead of having gravity drainage, you have pressure fluctuations based on the compressibility of your aquifer system. And that's important because the storage coefficient in an unconfined aquifer, these numbers are just for generic unconfined and confined. The storage coefficients are orders of magnitude different if you have an unconfined aquifer versus a confined. So in the Columbia Plateau system, there's 4 primary layers. There's an unconsolidated a layer of unconsolidated sediments in the overburden, and then these 3 primary basalt layers from the Columbia River basalt group. These storage coefficients we took from the literature. And so right away, you're going to see that there's a difference in the amount of storage change in these 3 confined layers, even if you have the exact same change in your water level in your well. Let's say you have 1 meter or 1 foot change in your water level in your well, you're going to have a lot more associated storage loss in the unconfined than you do in the confined. And this becomes really important in comparing what GRACE is telling us is being seen from storage loss versus what is actually happening. So simply, well, in words, I guess, for the most part, the storage change from GRACE, remember, this is that groundwater bucket. It's just the total changes that are being observed after you subtract out all the other stuff. The other stuff being your soil moisture, snow, and surface water. And so what we want to compare directly is this GRACE-derived groundwater bucket to the groundwater storage changes as a function of changes in the water level in observation wells. And again, importantly, the CPRAS is not a bucket, and we've known this for a long time. So this is a well-known paper work from 1974, where already there's a delineation between different aquifer zones, aquifer layers. This is pulled from the USGS report, where we have this pink is the Grand Ronde Formation. This is from a cross-section toward the center of the Columbia Plateau system. And then we have the Wanapum layer here. The light blue is the Saddle Mountains. And then the overburden is much shallower. It's thinner as a layer vertically and less spatially extensive than any of these other layers. So with my professor academic hat on, I was curious if the GRACE storage changes are able to detect any of the well-known groundwater declines that have been observed over decades in some instances in these deeper basalts. So let's look at that. First, I'm just showing here the groundwater anomalies in just the sum of the three confined layers, those Columbia River basalt group layers, the Wanapum Saddle Mountain and Grand Ronde layers. We see a very clear, statistically significant declining trend. This is, again, based on observations of groundwater levels in wells that we've converted to storage anomalies. And importantly, too, you note that the y-axis for this blue line is on the right, and it's orders of magnitude smaller than the y-axis on the left. This line, I think, represents well what we know about the confined layers collectively in the plateau, in the Columbia Plateau, which is that we've been observing long-term declines. Now I'll walk you through this spaghetti mess. So now I have added in two additional lines on the top with these red error bars and the stars is that GRACE-derived groundwater bucket. So GRACE minus the other stuff. This is what we're left with. We're working on the annual time step now, so we can more appropriately compare to observations. And then on the bottom here with the circles and the pink confidence intervals, these are the 95% confidence intervals, we have the sum of all the groundwater layers. So the overburden, that unconfined layer, and the confined layers. So a few things to note about this. First, both the GRACE-derived groundwater storage anomalies and the observed collective groundwater storage anomalies are on the same order of magnitude. And that makes us infer, or it implies, that GRACE is really observing just the changes in the unconfined portion of the system. This blue line, the confined, which is what matters to people who have wells, is just noise in the GRACE signal. I didn't even bother putting the uncertainty bars on here, although we have that elsewhere. They just end up inside the confidence interval of GRACE. And in other words, there's not a statistically distinct signal from the confined portion compared to the GRACE observations. Another thing to note is that where these red and pink confidence intervals overlap, the GRACE observations and the cumulative groundwater observations from wells, where they overlap, these time series are statistically essentially the same. And where they don't overlap, they are statistically different. And so that's the case for most of these years. In most of these years, GRACE is not capturing the observed groundwater storage anomalies that we have from the extensive groundwater monitoring network in Washington. And then we also pulled in data from Oregon Department of Water Resources and Idaho also. And then also we even have some years like in 2008, where GRACE says groundwater storage is going up, but the observations tell us that groundwater storage is going down. And so when I said at the start that this talk is going to be about healthy skepticism, about cool, shiny tools, this is what I mean. A lot of people, myself in the past included, have used GRACE satellite observations to study groundwater and to say that massive declining trends are attributable to non-renewable or confined groundwater declines. And this work is showing that that is not the case, at least on an annual time step. And so then that tells us that problem one with GRACE and using it for useful things, by useful I mean outside of academia, based on our work, GRACE is not capturing the confined groundwater signal. That signal is just too small, and it is too small because of this equation down here based on the storage coefficients for confined groundwater. Again, this is just the generic range for confined and unconfined. And hydrogeologists on the call might be saying, yeah, we knew that. We've been trying to tell people that, and that's true. But very little work has been done in academia to actually prove that that's the case. And so that's where this comes in. So then as part of this work, I wanted to say, okay, well, what would that confined head variation need to be in order to be detectable by GRACE? Maybe we're missing something in how this analysis has been done. And so I just took this original equation of how to get storage changes on the left from the head changes observed in wells, and took the accuracy of GRACE as 1 centimeter per month. So if we just take 1 centimeter and divide it by our storage coefficients, then this is what the monthly change in head would need to be in a well in each of these layers in order to be detectable by GRACE at that plus or minus 1 centimeter of storage change. So in the overburden, in that unconfined, if you have about a 1/4 foot per month, then that storage change is detectable, at least in theory, right? But then if we look at these head changes in the confined layers, we're working on installing more pressure transducers. There are already a number of pressure transducers in red here. Now, these dots are, sorry, this is so small. These dots are locations of monitoring wells used in this analysis, separated by aquifer layer. And then the red triangles are where there are pressure transducers. Here's just one well pulled out of the Spokane region. So you can see what a higher temporal resolution variability looks like. So what the ups and downs look like closer to monthly data. And unsurprisingly, we are not seeing head changes of 1,000 feet per month. And I don't anticipate that to be the case. That's pretty unrealistic, right? And so even if we look at larger seasonal drawdowns as opposed to the annual equilibrium measurements from spring to spring to spring, the head change required to be detectable by GRACE really does not show up in a realistic way in this conceptual exercise. The other problem with GRACE is, in terms of being used for any sort of management decision, is that not only does it not capture or separate out that bucket into the aquifer layers, it also, based on the spatial resolution, can't capture spatial variability in groundwater levels. So here, each of these hydrographs in black is sort of the well we were looking at. And then we looked at 1 mile, 2 mile, and 5 mile radiuses around that well to look at the hydrographs nearby. And then separated those by aquifer layer. So these two wells on the left, we'll just focus on the left here. These two wells are spatially quite close. They're open or screened to different aquifer layers and are showing really different historical behavior. This is back to 1975 or so. And GRACE just cannot capture this type of spatial variability. So if you wanted to know where should I put a well or how deep should I put a well, GRACE absolutely is not an appropriate tool for that. And I don't think anybody has said that it should be, but people come close to trying to say that. I'll just briefly touch on the fact that there's quite a bit of work to downscale GRACE data. So instead of those 100-kilometer by 100-kilometer grid cell blocks, how can we make higher resolution GRACE data? There's two main approaches to that. One is through something we call data assimilation. So instead of a traditional calibration validation approach to changing parameters in a model, data assimilation sort of does more real-ish time corrections to those parameters when you have observation data available. So we assimilate GRACE into models and hope that that corrects and then disaggregates GRACE into the component water budget parts. And then there's a bunch of machine learning approaches to downscale also. And the important takeaway here in this slide, this is just an example of the machine learning based downscaling approach for GRACE in California's San Joaquin Valley. I'll jump to this part of the quote. Our modeling approach was unsuccessful in simulating groundwater change in new time periods or over new spatial domains. So in my mind, there are not yet downscaling methods that are appropriate to use GRACE. Data assimilation, this is from a PhD student of mine who's on the call. Thank you, Sasan. This is actually just jumping briefly to High Mountain Asia, where we have simulated groundwater storage changes in this darker pink color in the Indus, Ganga, and Brahmaputra basins. And this is with GRACE data being assimilated into the model compared to observations in the lighter pink. And you can see that for the most part, even with data assimilation, the model is still not performing well in terms of simulating groundwater. And part of the problem is that a lot of the models that use this don't represent groundwater at all or well. So I just kind of cut this off here. This model that used GRACE for assimilation to improve its groundwater performance only had an unconfined aquifer layer. So Sasan's working on adding a confined aquifer layer to see if that more fully captures the variability in the groundwater system. This is something that I would love to bring to the Columbia Plateau Aquifer system as well. So where does that bring us and where have we been? The figure on the right is from the 2021 Long-Term Water Supply and Demand Forecast project, along with some partners on this call and Aspect Consulting. We looked at where groundwater rights have been issued in the gray dots and higher density in these orange blobs. And blob is a formal term. And then where we have existing monitoring capacity, mostly through Department of Ecology, in the bluish and greenish blobs. And so our goal with this was to try to increase the number of groundwater observations we have and data being collected where we know groundwater rights are being issued, but we have limited monitoring capacity. This is a picture from here's Tracy Band, multiple conservation district partners on a training day to train conservation districts how to monitor groundwater and to provide the equipment. This is an ongoing program. But the next step to this was for semi-annual monitoring. So having conservation districts monitor groundwater levels in spring and fall. And what I'm working on now and would love anybody's help who is on this call is installing pressure transducers in, well, any well that we can, basically. I have the funds in part through this grant. I have transducers already. And so we want to be able to capture higher temporal variability in groundwater level fluctuations to really make sure the analysis that has been done so far for GRACE, so from an academic perspective, to make sure the analysis that has been done so far for GRACE is accurate and to see if there's anything else that we can learn in comparing ground-based remotely sensed observations. And then from a management perspective, to better understand the recharge and discharge dynamics of groundwater throughout the growing season. It's great to monitor the long-term status of an aquifer system, but that doesn't help us understand where water levels might drop to in July, August, September at the end of the growing season. And so I'll use this time as a call, as a hope to anybody who has locations that could have pressure transducers to monitor those. And also, I have instruments for volumetric soil water content, soil water potential, and weather to basically monitor the full water budget at point locations across as much as of the Columbia Plateau system as possible, to better ground truth our remotely sensed observations and to hopefully more holistically have tools to understand the role of groundwater in the water budget for management as well. I think with that, for time, I'm just going to leave you with my favorite cartoon and open it up to questions. Thank you.